All right, so it took me a little while to figure out what kind of algorithm I wanted to talk about in this presentation today. I thought about a couple of the computation-heavy stuff that we talked about in class and in the lectures. The multiplication through addition algorithm and things like that, where you just walk through a bunch of math. And I thought, I thought I would do something that's a little bit more interesting to me. It is a computation-heavy algorithm, but something that's a bit complex for a presentation, but I think it's really fascinating and requires a lot of understanding of algorithms in general, although is a bit higher level of a presentation today, as the nitty-gritty of this is pretty insane. But the algorithm I've decided to talk about is ray tracing. The algorithms involved in ray tracing, which I don't know if anybody here has played any video games or is much of a gamer or has kept up with gaming, but something that you hear a lot nowadays is you hear the term ray tracing. You hear the concept a lot nowadays whenever you hear about graphics. And to kind of put everything in perspective, I thought it would be kind of fun to look at two pretty direct comparisons. The image on the left is the original Doom, what a lot of people say is the very first-person shooter game. And this came out in the early 90s, 93 or 91, 92. And the image on the right is the newest Doom, which came out a couple of years ago. You can tell, although the image is a bit pixelated from on the right, the one that I pulled, it looks quite a bit higher res in the game itself. But we've made some pretty serious leaps and bounds in graphics and gaming technology. And it's literally all due to complex mathematical algorithms and the increasing of our processing power. It's not because we didn't understand graphics, necessarily that the early 90s were so rough. Computers could not do the things that they can do nowadays. And I think that the gaming industry is a really interesting perspective for computing because, 90 to 2016, that's what, 26 years between these two. It's like half of a life, fourth of a life. Many people have, been around before these graphics were even capable, and now we're seeing these crazy, almost photorealistic stuff, which is, partly due to ray tracing. So the first, and this is once again just a little bit of background before we start talking about ray tracing itself, but the concept of computer graphics was first coined back in 1960. So that's 60 years ago, so not very long. The first game, Space Wars, what a lot of people argue is the first game. Space Wars came out in '61, and then the actual concept of ray tracing, which once again we'll go into more detail in a minute, actually dates back to 1969. So long time ago, we've understood that ray tracing is possible, but it hasn't really been implemented until recently. And to just once again give a little bit of perspective, Doom, that original game on the left, came out in '93. So quite a bit after that was that game, and then less than the time between, or approximately the time between, the conception of ray tracing and the first FPS, we now have, these crazy graphics. And one reason why ray tracing has been understood for a long time but not implemented is the processing power and the hardware that's needed to actually complete it and to accomplish it. And I pulled just some specs from NVIDIA on some of the more recent ray tracing requirements for the PlayStation 5 just came out, or I guess about a year ago. And one of the big things for the PS5 for the home consoles was that it was capable of pretty intense ultra graphic ray tracing. But from like a computer component side, you need a very updated NVIDIA RTX for 1080p, but with relatively low detail. And if you want to get things up to ultra, to the super realism, the very photorealistic stuff, you need the 10 gigabytes of VRAM and a pretty intense Intel Core processor. All of these are pretty recent. They definitely did not have them in the 90s. So now that we've kind of talked about the background of gaming and the computation power that's involved, we can start talking about ray tracing itself, which from a very top-down, far out perspective, it's pretty simple. It is just the concept of light hitting something and then hitting your eye. That is how eyesight works. If we didn't have light, we wouldn't have sight, and the reason for that is because it reflects and refracts off of everything around us, and we interpret it through our eyes. So, like the idea itself is pretty simple. It's just, I think philosophers figured this out in like the 1600s. They didn't necessarily know what light was, a particle or wave, that kind of stuff, but they understood that, without light we can't see, and it bounces off of things. So that's what you're doing in a ray tracing algorithm. And there's the original way, which is maybe the kind of what you would think would be the most straightforward way to do ray tracing, is what they call forward ray tracing. And that's what you see here with this image. It's you measure where the light comes from, hits an object, and then enters your eye. But the following of this photon forward into your eye is computationally a lot more difficult, because it can refract and reflect off of that surface in a bunch of different ways, as well as, you don't necessarily know which one is going to hit your eye immediately. So the way that you get around this is a concept called backward ray tracing. So in backward ray tracing, you do the opposite. It's a bit more like, kind of like egotistic in a way, like we know where the camera is. So instead of passively receiving the photon, the quote-unquote photon, the emulated concept of the photon, we actually use from the camera or the eye to the light. And you do that through the object. So this is backward ray tracing, tracing from the eye or camera to the origin of light. And the ray from the eye is traced to an object, whether it be flat or circular, opaque, otherwise. And then the line is traced back to an origin of the light. If there is no light, then there is no visual. And if the light is obstructed, the ray of the object, or not necessarily just obstructed, but the secondary ray that comes off of an object towards either another object or a source of light, is called a shadow ray. So when implementing this algorithm, like it makes sense kind of inherently that we're just bouncing, the physics of bouncing something off of another object, light or otherwise, is pretty well understood. It only really has two steps from a high level, and that is to determine if a point is visible at a pixel, which you'll see a little bit in a minute. Then shade the point based on the light source and intermediate objects. So you literally have like a set of pixels in front of you, if you can visualize it, and you can see it a little bit better here. We have the pixels that are creating the image that is being viewed by this camera, and you essentially shoot what are called primary rays into an object, and then bounce off of that object the shadow rays, which can hit either another object or can hit the light source. So once again, simple vectors, angles, not that hard from a conceptual level, The issue and why we in early 2020s are still talking about ray tracing is that the computation speed and power that's needed to run these in real time, especially for video games, is incredibly high and very difficult to compute and use. The algorithm itself can take less than 200 lines of code, but the amount of time to determine the point-to-point correspondence of the projection and scene is quite high if you don't have a computer with high enough processing power. So once again, this is why it was discovered in the late 60s, 50s, but only recently is being implemented to its fullest. So whenever we're beginning this algorithm computation, we have a few factors that are set up that we know. We have the camera position, we have the view direction, the way that the camera is facing, the camera orientation, so angle, things like that. And then we have the field of view and aspect ratio, so how wide are we looking, how tight is the quote-unquote lens of this imaginary camera. And then we know the distance to the image and the resolution. And then, using all of those factors, we can start calculating where the rays are going to hit and where they're going to bounce from. So for each pixel, a primary ray is emitted into the scene. You can see with this little black line here through the middle of this pixel. And this is done for thousands and thousands and thousands, so that's why we're talking about this processing power. It's then determined if the primary ray hit an object in the scene, and if it does, a shadow array, so this one, is then ejected, the one coming off of the big ball, is ejected from the object hit by the primary ray, and then depending on if the shadow ray hits an object or the light, the pixel is emitted. So each ray is essentially just a vector that's thrown from the eye or an intermediate object, and when the ray hits an object, the angle at which the ray hits, the opacity, the color, all of that stuff is used to determine the angle and it's the intensity of the ray that comes off of it. So here, if it's a black kind of opaque surface, it won't reflect light nearly as much as a silvery reflective surface. And so the object itself, its opacity, color, reflectiveness is relevant. And then on top of that, the angle of the refracted ray is relevant and is determined using the angle of the primary ray as well as the surface of the object which is hit by the primary ray. If the surface is flat versus curved, the ray will reflect differently, and the intensity of the shadow ray will change depending on what objects are between the first object and the light source. So there's a lot of stuff that goes on to get from one object, one camera, all the way to the light source and back, which is why the computation complexity of the ray tracing problem is very high. And the challenge to getting from this concept, the 1969 concept, to today is treated as the ray tracing problem, which is being solved pretty well nowadays, honestly. And the more geometry there is in a scene, the more complex and time-consuming the algorithm is. So it's really interesting to see how this concept of an algorithm, which is relatively straightforward, can take so much time and so much processing power to implement in code, as well as through the computational power of a computer. Although we've known about it for decades, only recently have our computers been capable of implementing our algorithm, of implementing this ray tracing. So that's my presentation. I hope it was interesting. I know it was a little high level, but the depths I would not have had 15 minutes. You can't really. There are classes and courses on ray tracing, but this is a nice little overview of what this computation actually goes through. So hope you enjoyed.